In the next section, we'll look at suffix trees, a way to get an index built when we don't have words in our text. And I want to motivate them first by showing a slightly different problem that they will, in the end, solve as well, and where it seems an efficient solution is really hard to get. So that's the problem of finding the longest common substring of a set of strings. So you're given a set of strings, can be many k strings. There's a small example with 2 strings, and your goal is to find the longest substring that occurs as consecutive characters in all of those k strings. Okay, so if you have these 2 Soup California Lives and Sea Liver, what's the longest thing that occurs in both? I think a life is the longest, just because the second text is relatively short. There's not so many possibilities. And here we have 5 characters, and that seems not to be able to do better. But now imagine if you have many strings, not just 2, and all of them are long, and they might overlap in arbitrary ways. So this is all about can be worst case. How should we find such a longest common substring? Now, in principle, the problem is easy. You can go through all possible substrings of all strings, all start-endpoint pairs, and check for every substring if they occur in all the other strings. We've seen string matching algorithms to do that in a somewhat reasonable time. But it feels like this is at least quadratic in the length of these strings, and maybe worse. Whereas the question is, can you do it in linear time, linear in the total length of the strings? That's the same time as just reading every string once up to constant factors. And it seems if you look at this, not possible. But indeed, it is possible, and suffix trees solve this. And it's not even a complicated algorithm to do it. We'll see it next time. Suffix trees are much more versatile than that. They seem to be the kind of go-to step, or the threshold concept that you need to solve many string matching problems or string problems in general. They're very fast to construct and use. That's not obvious, but we'll come to that. They can be constructed in linear time, and they take up linear space in the length of the string, or length of the total number of strings. Total length of the strings. And here's what I alluded to earlier. Donald Knuth is one of the maybe founding fathers of theoretical computer science. He wrote this famous book series, The Art of Computer Programming, that defined many of these things. And he's also the author of Tech and what is behind LaTeX. And in the 70s, Don Knuth, who has good intuition about many things, maybe, conjectured that finding this longest common substring cannot be done in linear time. And he was proven wrong by the invention of suffix trees in the end. But it took people a while to get the algorithms fast and eventually also simple. Okay, so what is a suffix tree? The definition is actually simple. The suffix tree for a text is just the trie of all suffixes. Now, a few nitpicks. We'll use the compact trie because the other one takes too much space. We'll always add this end of word marker to our text. That's just to make sure that if I take all the suffixes of a text, these are a prefix-free set of strings. Other than that, the definition is straightforward. There's nothing special about it. So let's have a look at an example. I started drawing this in the break, and we'll build the rest together. So here's a text, banana. I already added the $, and I already took all the suffixes, which just means deleting one more letter from the beginning, one after the other, until you're left with nothing. And so we have the suffix starting at position 0. We have the suffix starting at position 1. and 2 and 3 and 4 and 5 and 6. Right, so these are the indices in the string. To build the compact trie straight away is messy, but it's easier for the example to do it. Also, if you want to do it manually, it's easier to first build the standard trie and then compactify it afterwards. I've already started inserting the longest suffix, banana, and then anana down here. Let's do the next one, nana. We start with inserting from the top. There's no n at the root so far, so we add another edge with n. And then, because we don't have any other paths on that part, we just append the remaining letters. And here I'll just put the starting index in the leaf, so I don't have to copy the entire string. We'll use that later too. The string is stored once, but then I don't have to copy the suffixes in each point. I just need to know where they start. So that's nana inserted, then anna. For this one, we started the root a, n, a is already there. The only thing that's missing is now the dollar. So I just append that here. And that was number 3, starting index 3. And these get shorter and shorter, which helps over time. So if you insert NA, we go NA already in there. So we just add a new edge for the dollar symbol. Then 5, A, and then the dollar. And for 6, we just have the dollar. So that in that example, it also shows how the trie makes use of repeated parts in this text. Right, if you want to compactify this, all we have to do is get rid of all the unary nodes. So we start with the root at 0, then we have 4 edges for dollar, for A, for B, and for N. All of these, well, this one leads to a leaf straight away. A leads to another internal node, and we haven't skipped over any characters. B skips actually all the way along and goes to a leaf. And N skips 1 position, so we continue at index 2 when we read further down, and we're actually now at this point. So let me maybe indicate this. So we're here at this guy, whereas this one's that node. And okay, it might get too messy to connect it with all, but I can try. Okay. Let's continue with this node, so you see how we continue there. We have one edge with the dollar that goes to leaf 4. We have the other edge that goes to the other leaf 2. And we only need the first letter N. Then what's left is this node. So we jump here. We again have a branch of 2. Either we go with dollar to the leaf 5, or we go with N to another internal node, but we jump 2 down. So we go to index 3. If I want to highlight this, yeah, now it's getting messy, I guess. Let me get rid of those. The leaves are clear because they have the same label. So that node here, again, we have a branch of 2 nodes. We have the dollar for a leaf, and we have another leaf indeed, where we go with N. And that's it. So the compact trie is visually much smaller as well, right? It's much shorter. So that's a way to build the suffix tree. This guy here on the right is the suffix tree for the text banana. The only problem with the procedure I've shown you is we first build this standard trie, which is quadratic in size, n times m, but m here is the number of suffixes, that's another n. So this guy here can have n squared nodes, internal nodes, as we've seen before. So even if I'm smart about the second step and the first step of building this tree, the intermediate step makes something so big that the overall time will be quadratic. So this procedure is fine on small examples, but it doesn't scale well to large texts. Here's another example drawn a bit more nicely and slightly bigger. And I've drawn it sideways so I can write the text in the normal way. Other than that, there's nothing different. Now, this shows you the human representation of suffix trees that I'll use on the slides to introduce algorithms. The human version differs from the actual one that we represent in memory in a few cases. We store the actual suffix in the leaves so that you can read the text instead of having to jump to the starting position. And on the edges, I write down the entire string that they represent. Remember, this is a compact trie. There's only one string that they represent, but it would normally not be stored explicitly. We would just store the first character. But to make it nicer to read for us and reason about it for us, we'll have the entire edge labels. What's actually stored is this. Right? So step one is we represent the leaves by the starting index, not the string. And step two is use the convention for compact tries we've had earlier. So these are all hidden. But we'll use the human readable version to design algorithms because it's much clearer to see in the examples what happens. But you should keep in mind this is what actually is stored. I've mostly discussed this already on our example, but to have it in proper writing, if I have a text and I append the $, it has n+1 suffixes because I added one more symbol. We can build the suffix tree easily via the route I've shown you by inserting one suffix after the other in a compact trie, or for that matter, build the standard trie first and then compactify it. Both gives you quadratic time, and it turns out that that's not interesting. You can do in quadratic time, you can do other things, and flip side is most interesting applications become infeasible if you require quadratic time in the text size. So for example, your genome is 2 billion characters. If you square that, it'll just never finish. Now, the amazing result I already alluded to is you can find the suffix tree in linear time, even though it seems to need inserting many, many suffixes. We'll come back to this. We'll, at the very end, actually see an algorithm to do that. It was long conjectured, or it was a surprise when it was first discovered. And we've seen this comment from Donald Knuth that he conjectured it not possible. And by now, they're a staple method in practice, especially for genomic analyses. They build on techniques that we'll discover here routinely. For the moment, what we'll do is just assume that we have some magic black box that gives us the suffix tree in linear time. And before I tell you lengthily how they are constructed, I want you to be able to see why they're useful. So for now, we'll just take that for granted and look at some applications of suffix trees. Before we go to that, we should probably make sure that this definition is clear. So it's a lengthy question, but it's a good prompt to discuss a few nitpicks as well. And I'll go back to the example. I think that's useful. Would be lovely to get to 60 again. 5 more missing. And one more. Yay! So most answers got some votes. Not all are correct, but quite a few are. Let's briefly go through those to discuss. So we said this, that's just our convention always for suffix trees, and that's something most of you got right. The size of the suffix tree is never quadratic because it's a compact trie. And that one, even in the worst case, is linear size, linear number of nodes, and constant size per node if we assume the alphabet is constant. It is true that the suffix tree is the compact trie of all suffixes, but not the standard trie. That would exactly be too big. The leaves kind of represent the suffixes, but they don't store a copy. That's why with that addition, that's clearly not what we want. Again, otherwise we'd need quadratic space. They just store an index, the starting index of the suffix. We've seen the naive construction. I commented on this many times, and I added the claim that it's possible to do it faster. The last one is kind of mean. It's n+1 leaves, because we have n+1 suffixes, because we added this end of word marker. Other than that, it's almost correct, right? But yeah, not quite. Good.